seminar on the organization of the whole semester, which is very fine. And so I'm going to speak about a topic which is related to this semester. I will consider some overdetermined free-boundary problem, which is a classical class of free-boundary problem. Overdetermined means that I will consider both Dirichlet and Neumann condition on the boundary of the domain. And I'm looking for the shape omega, which gives a possible solution of this overdetermined problem. So this is a joint work with two colleagues from Firenze in Italy, Chiara Bianchini and Paolo Salani. And I'm going to make some advertising for a method to prove existence of solution for such problems, which is inspired by shape optimization methods. And I will explain why, in general, this kind of variational method can help to solve this kind of overdetermined free boundary problem when there is a variational formulation behind that. So let me start with a motivation, which could be the classical Serrin problem. So James Serrin, in a very famous paper, which is more in the context of symmetry problem, proved the following. If you consider the solution of the very simple PDE minus Laplacian u is equal to 1 in the domain, u equals 0 on the boundary of the domain, and this is this PDE I will consider during the whole talk. Okay? And if you assume, moreover, that the gradient of u is a constant over the boundary of the domain, and if you assume regularity, because in this original proof, it needs C2 regularity of the boundary of the domain, then the only solution, the only possible solution omega for which such overdetermined problem, and you see now why I call it overdetermined, because I have both Dirichlet and Neumann boundary condition. The only possible solution for which this problem stands is the ball. And obviously, since it is the ball, we know explicitly the solution of the torsion problem. And in his original paper, James Serrin used the moving plane method, which has been introduced by Alexandrov, actually, to prove property of surfaces, namely that if a surface has a mean curvature which is constant on the whole boundary Z, it has to be a wall. So this moving plane method is applied for the first time by Serrin in a PD context, and using strongly the maximum principle, he is able to prove that the domain omega for which this problem has a solution has to be symmetric with respect to any hyperplane. So it has to be a wall. Later, there are many other proofs of this result. Even in the same journal, there is a short paper, 2 pages by Weinberger, who gives an alternative proof. I suspect Weinberger was the referee of the paper by Serrin. So he found this alternative proof, which stands on some integral identities, and there are many other proofs of this result. Of course, the Serrin result applies for more general PDE, even nonlinear PDE. The moving plane method can be applied for such problem. So this is my starting point, and I just want to replace the constant gradient on the boundary by a more general overdetermined condition. So my question is the following. I consider the same PDE minus Laplacian u is equal to 1, u equal 0 on the boundary, and I assume that I know, I have a supplementary information that the gradient of u is given something, obviously not constant, otherwise the answer is already known. And I would like to know if we can say something, if you can find omega, if you can give some properties of the domain omega and so on. So if I assume that this Neumann boundary condition is not constant, of course the domain will not be a ball. But I have to mention that there are some results claiming that if gradient of u is no far being a constant, there are some stability result in some sense of this free-boundary problem. If gradient of u is not far to be constant, then omega has to be close to a ball in some sense. And there are several papers in that direction. The first one I know is the one by Amandine Talion, Jérôme Busca, and Wolfgang Reichel, who gives exactly a measure of the distance between the domain and the ball in a regular context. I wrote a similar paper, but it was in the case of a ring with Philippin and Prévert, and there is a more recent work by Brandolini, Nietzsche, Salani, and Tombetti, also about the same topic. And at the end of my talk, I will give another theorem in that direction, namely the stability of the Serine problem. It will be my concluding theorem. Okay, so our problem is the following. We consider a given J, which is with positive value, and the question is, can we find a domain omega such that there is a solution for this overdetermined problem? And maybe let me just make a short computation, an easy computation to convince you that it is by no means a trivial question. So let me consider the radial case. Assume g of x is radial. Depends only on the distance to the origin. So with J from Rn to R plus, and I will assume for this computation that J is non-decreasing. Okay. And so we will see later that in that case we can prove that if there is a solution to our overdetermined problem, this solution is necessarily a ball centered at the origin. So let me denote CDR, the ball centered at the origin of radius R. So using the symmetrization argument, rearrangement argument, we will prove it later. Okay, so now if the domain is the ball, we know explicitly the solution of the problem. I already wrote it. In n dimension, it is this radial function, r square minus modulus of x square divided by 2n. Therefore, the gradient of u on the boundary of the domain, the radial derivative, so you get r over n. It's 2r over 2. While, so you remember that the overdetermined boundary condition I want to satisfy is gradient of u is j of x. But j of x is g of r. Here. And so you see that according to the possible value, so here you have the line r over r, and here you have the function j of r. And obviously you can see that according to the choice you do for the function j, you may have no solution, no r which satisfies this. You may have an infinite number of solutions. You may have a unique solution and so on. So it depends, it really depends on the shape of the function g, for which the number of solutions will be a consequence of this computation. Here, as soon as we know that the domain has to be a ball, the only thing we have to choose is the radius of the ball. So you have just to solve this 1D equation. And so you see that the number of solutions strongly depends on the shape, on the geometry of the function. Okay. So we expect that the problem is not trivial, and we will make some restrictive assumption on J in order to have existence and possibly uniqueness and so on. Okay. And so precisely the question we are interested in, I will probably, to have the notation fixed, so the problem I'm interested in, I recall it here, my overdetermined problem, this one. The following it is called 0.1. Magnetic Laplacian u is 1 in omega, u equals 0 on the boundary of omega. The gradient of u is j of x on the boundary. So the question I am interested in are obviously the question of existence of a solution, possibly uniqueness of the solution, regularity of the solution, and also some geometric properties. Namely, can we say something about the geometry of omega, the solution of this problem, with respect to the properties of J? If J has some convexity property, can we prove that omega is convex and so on? So these are the questions I'm going to discuss in this talk. Before that, let me mention that there is a very related work by Björn Gustafsson and Henrik Chagulian. So Henrik is not here today, but he knows our work. So it was a paper which is almost 20 years ago, where they study exactly the same problem. I mean the same overdetermined problem with f, which is instead of my 1, so it looks like more complicated, except that their f is a function of a measure, and they assume, and they need to assume that the positive part of f has compact support. And this makes a real difference between our two situations. I will explain below why. We are not able to use their technique because of the 1, which is not compactly supported. Okay? And in their case, I think that they always have a solution. And as you see, in my case, I have not always a solution. Okay, so notations for any domain omega, I will denote by u omega, the solution of the PDE. So u omega is what we call the stress function or the torsion function, which is the solution of minus Laplacian u omega equals 1 in omega, u omega equals 0. Which can be defined for any domain omega, and there are several variational formulations to define this u omega. You can see it either as a solution of the variational problem, integral of grad u, grad v equals integral of uv, for any function in the sub-LF space h10, so h10 is a set of function in h1 which vanishes on the boundary, in the sense of the trade, for example. And it's well known also that you can characterize this u omega as the minimum of this natural energy associated to the problem. So u omega is precisely the function v in h10 which minimizes this quantity. And what we call the torsional rigidity of a domain is precisely the integral of u omega, or the integral of gradient of u omega squared, which are the same using the variational formulation when you plug v equals u omega, the variational formulation. And you see that because these two quantities are the same, when you compute the natural energy J at the solution at u omega, you get 1/2 of gradient of u omega minus integral of u omega, and this since these two quantities are the same, you get minus 1/2.
So formula
The
03, there is something wrong, right? It's integral of V in the last, right?
Yeah, right-hand side.
Oh, yes.
Yeah,
Oh, yes.
yeah.
Just to show
Let
that
me
we
take
don't
a.
swim. We
You're
are-
right, you're right.
We are away.
Okay, so this torsion or torsional rigidity is a well-known quantity for which many studies have been done. And in particular, one of the studies is one of the first shape optimization problem is the so-called Saint-Venant problem. The Saint-Venant problem consists in looking for a domain omega of given volume, say, which maximize this torsion. And if you look at the simple elasticity model for which the torsion represents precisely the torsional rigidity of a bar of section omega, the question was, for a given bar, what is the shape of the section which gives the best torsional rigidity? So this was the motivation by Saint-Venant in the 19th century when he asked this question. And obviously, at least for heuristically, we can expect that the solution is given by the ball, and Saint-Venant probably already said that the solution should be a ball. And it was proved only in 1948 by Polya that the ball is the solution of this shape optimization problem. The ball maximizes the torsional rigidity when you assume that the area of the volume, when you assume that the volume of the domain is fixed. And the proof is obviously using symmetrization, so let me write it, the proof in 2 words. So you remember that here I write the energy of the problem, and you remember that the solution of my PDE is the minimizer of this energy. So if I consider any domain omega, and I choose omega star, the ball of same volume as omega, and I introduce U star, which is the symmetric decrease in rearrangement of U. It means that it has exactly each of level set of U star has the same measure that the corresponding level set of U omega, but for U star these are balls. So we have this decrease in rearrangement. Now you write precisely the fact that the torsional rigidity of omega star is obtained as a minimum of my energy. So it's less than this quantity because U star has no reason to be the solution of the torsion problem on the ball. It's just a test function. So you just write that the energy is less, the torsional rigidity is less than this energy. Now you use the classical property of the rearrangement. So the Polya inequality tells you that the Dirichlet energy of the top of the rearrangement is less than the Dirichlet energy of the initial function. And equimeasurability tells you that the integral of U star is the same as the integral of U omega. Now, since U omega is precisely the function for which the energy is minimum, this is exactly equal to minus 1/2 of T omega. And so you have seen that you start from any domain omega, and you have proved that minus its torsion is larger than minus the torsion of the ball, which gives you the result. Okay, so now what I want to do is to solve the same problem, at least to study the same problem, maximization of the torsion, but replacing the constraint on the volume by a new constraint, which is this one. Integral of G square, J is given. Integral of G square is less or equal to 1. Or if I want to work in a minimization process instead of a maximization process, I just have to take G of omega minus 1/2 of T of omega. I introduce, so my constraint will be just to say that this functional of omega, phi of omega, is less or equal to 1. And so my shape optimization problem, I want to consider So my S-shape optimization problem is to minimize G of omega with phi of omega less than 1, where G of omega is minus 1/2 gradient of U omega squared. U omega is the solution of my torsion problem. And phi of omega is just the integral of J squared. And so I want to solve this one, and I want also to show you why the solution of this problem will give the solution I am expecting with some assumption.
Could you please determine the energy? J doesn't come.
So either I'll write it like that or like that.
Oh,
It is the same just because. That's funny that the video stops as soon as I rise. Okay, so I want to solve this problem. So what are the assumptions I am going to consider on my density J? So finally, I replace the Saint-Venant problem by a new problem with a density. And let me explain what are the assumptions I put on my density. I will consider two kinds of assumptions, the strong ones. So
I'm sorry, one question. Your omega is unknown, right?
my omega is unknown, but
Your G is given in all Rn, right? So you write the condition with omega, right?
I am looking for some omega which minimizes this G. G of omega can be defined for any omega. You see? You just take any bounded omega, you solve this,
Yeah.
you compute my G of omega, and you just check whether this constraint is
Omega
satisfied
is
or
okay.
not. So for any omega, you can compute G of omega, you can compute phi of omega. If phi of omega is satisfied, you can look at the G of omega and check whether
This is
it's
my
a
question.
minimization.
G of omega is the G is a given function on Rn, or it's the
My J is a given function
Yes.
on R. Yes.
Okay, thank you.
But yes. And so I can compute this, yes,
Yes,
it's
yes.
defined on the whole space, so I can compute this quantity for any bounded domain. I get a number. So the strong assumption I will put is actually not the continuity assumption, which is quite classical, but it is the homogeneity assumption. I will assume J to be alpha homogeneous. And you will see immediately why I need this assumption. But I will also, so the homogeneity assumptions just mean that as soon as you consider any level set, say the one level set of my function G, you know the function everywhere just by scaling. So geometrically, the definition of J depends on the shape of this one level set. And all the level sets are obtained by scaling. Let me just say that actually I have two problems. I have my shape optimization problem, which is below, and I have my overdetermined problem, which is here. And the shape optimization problem is weaker in some sense. Namely, to solve the shape optimization problem, I need weaker assumptions. I just need to compute that G is, to assume that J is continuous, positive, and coercive in some sense, goes to plus infinity at infinity. And these weak assumptions on J are sufficient for me to prove existence for my shape optimization problem. And when I want to come from the shape optimization problem to the overdetermined problem, I need more. And I think it's my next slide, you will understand why. So this is precisely what I want to do. How can I come from the shape optimization problem to the overdetermined problem? So let me assume that I have been able to prove a solution of my shape optimization problem, which is there. So I have proved existence and I have proved regularity in order to be able to make shape derivative as explained by Catherine last week, because I just want to perform some shape derivative to write down the optimality condition. So since I am solving a minimization problem with a constraint, of course, the optimality condition reads you have a Lagrange multiplier between the derivative of the criterion and the derivative of the constraint. So it's what I wrote there. The derivative of the criterion dg is proportional to the derivative of the derivative of the criteria dg is proportional to the derivative of the constraint. What I denote dg omega is, I don't remember if you used this notation, Catherine, last week. It's the same, exactly the same notion that Catherine explained. By definition, the derivative of g at point omega in the direction v is the limit of the differential quotient g of omega t minus g of omega over t, where omega t is obtained from omega by some perturbation field and t small. So I have my domain omega, and I take a small perturbation of omega using a perturbation field. So my v of x is like that. I choose t v of x and so on, and I compute this differential quotient. So to be able to do that, actually we do not really need regularity, except that the expression I am going to write just use some regularity, because I need, as you will see, that the gradient is L2 on the boundary, for example. So I need either C2 regularity or a little bit less, or convexity, in order that the gradient of my solution here is in L2. I need that my solution U omega is in the Sobolev space H2. So I need, for example, C2 regularity or convexity to be able to claim that the gradient is in L2. Otherwise, the derivative always exists, but it is written as a domain integral, not a boundary integral. Okay. Okay, so more precisely, when we compute the derivative of g, assuming the regularity I just mentioned, we get this expression of the derivative of g, this expression of the derivative of phi. Obviously, when the constraint, the density j is equal to 1, phi is just the volume, and you get the derivative of the volume, the usual derivative of the volume. Okay, now if you assume that this first derivative is equal to lambda, this second derivative, you get a relation which is precisely this relation has to hold for any v, for any deformation field v. And so, obviously, the difference is orthogonal to a dense set in L2, so the difference has to be 0. I mean that this relation has to hold on the boundary of the domain, because v times n, the normal displacement, can take any possible value, at least a dense set of possible value in L2. And so the integrand, gradient of u square and lambda j square, has to be the same almost. Okay, so you see that I am not far from the overdetermined condition I wanted to get, except that I have this lambda, this Lagrange multiplier. And so I would be happy if my Lagrange multiplier is equal to 1, because now I have exactly what I need. But the problem is that
I just was a little bit confused about the sign. I mean, when you look at, I mean, you were looking at the minimum proper gradient
Yes,
u omega h. So it would be the maximum problem
for the torsion.
for this functional j of u, right? Because it's minus.
No, because this expression is the same than this one.
Fine, yeah, exactly.
And so, no, I am precisely minimizing this one.
You're minimizing this one?
Yeah. Yes,
You want to maximize integral gradient u squared?
yes.
Okay.
Yeah.
I think there is a minus sign missing in your shape derivative of j.
Of J?
Possibly, yeah.
No. Because it's the same.
You change
It's the same than the volume. Just take J. J. Sorry. Here you think there is a minus sign. Don't think so, because if you expand, if you have a domain omega and you expand it, the torsion increase
as the torsion increases, the energy is decreasing.
and the energy is decreasing. So you're right. Okay. That's maybe the why we use, yes. In principle, there is a minus sign here because it is minus the torsion. You're right. Yeah. I forgot a minus sign. Anyway, so we get some relation between both. But what I wanted to say is that my lambda is just a Lagrange multiplier then, and unfortunately, I'm not really able to control the value of this Lagrange multiplier. And so this is why I have to assume this homogeneity of the function j. Just at this point, it's a trick to be able to get a solution starting from a Lagrange multiplier lambda, which is, I don't know why. But obviously now, if I make scaling, so I have my omega, solution of my shape optimization problem. I make a scaling. Instead of omega, I consider t omega for some t. Now the torsion function is defined as t square u omega of x over t, which is the solution of my u problem over t omega. It's very easy to check. Its gradient is given by t gradient of u omega at x over t. Since gradient of u omega is lambda j, it's not lambda, actually it's square root of lambda, so I'm sorry. Anyway, it's proportional to g at point x over t, and you see that I just need to get j of x at the end. So now I use the homogeneity of j. J of x over t is t minus what alpha times j of x. So what you get here is t minus 1 minus alpha lambda j of x, and obviously you can choose t as soon as alpha is not equal to 1. You can choose unique t for which this product is equal to 1, and you have a solution of it. Okay. So, as you can see, so you can say, okay, the case alpha equals to 1, which appears to be problematic using this approach. Maybe just a problem of approach. You can change of approach and get something else. But no, I claim that the case alpha equals to 1 is really special. If you remember my computation just at the beginning, where I did this graph, and I put a graph of g of r here. Now, if alpha is equal to 1 in the homogeneous case, it just means that j of x is something like that. The only radial one homogeneous function are precisely this. And so you see that my picture of j of r is like that in that case. And so precisely either a, the constant I put here, is precisely 1 over n, and then every ball is a solution, or A is different of 1 over n, and there is no solution. So this is really one of the picture I presented at the beginning. There is 0 or an infinite number of solutions in that case. Now for any other value of the exponent here, you will get a unique solution for my picture, which is that. So this is what I mean by claiming that the case alpha is equal to 1 is really special. And my second remark relates to the approach followed by Gustafsson and Chagonian, which actually was inspired by the very classical paper by Alt and Caffarelli. Instead of looking at the shape optimization problem, instead of looking at the minimization of G with a constraint, they take a penalized problem, which is this one. They minimize the same G, this one, and they penalize by adding some constant times phi. And obviously the great interest of that is that you don't care about the Lagrange multiplier. There is no Lagrange multiplier because there is no constraint. So you get exactly immediately the overdetermined condition doing that. So it is the reason why it is tempting to do that. But what I claim is, in our case, there are choices of the function g for which this functional f of omega has no minimizer. Actually, the infimum is minus infinity. And so I cannot follow this approach if I just want to find a minimizer. Obviously, any critical point of f would give a solution of my problem. But it's not clear to get a critical point which is not a minimizer. In that case, it's not clear to have a Palais-Snail in the framework in that context. So this is the reason why I cannot follow the approach by Caffarelli or Gustafsson-Chagonian. And this is due to the fact that my f minus Laplacian u is equal to f is not compactly supported. See? This is related to that.
So you don't have coercivity?
Yes, in some sense. Yeah. Okay, so let me give the main result of this work. So if you assume that J satisfies the weak assumption which shows just coercivity of J, so I mean J goes plus infinity at plus infinity, then I can prove that the shape optimization problem which is below has a solution, and I can prove regularity, which is a classical regularity in that kind of problem, namely in 2 dimensions I have a full regularity, C1 beta. I cannot hope more because I have no. I just assume that J was Hölder continuous. So I cannot hope more than C1 beta. And in higher dimension, I can get C1 beta regularity for the reduced boundary, and the singular boundary is 0 and -1 Hausdorff measures, which are the classical regularity for those who know this kind of problem. And then, as I explained in my computation before, as soon as I have a solution of my shape optimization problem, and this regularity is enough to be able to compute the shape derivative as I did, then I can find the solution of my overdetermined free boundary problem by the trick I presented. And obviously, my overdetermined condition here is satisfied in general in n dimension, is satisfied only on the regular part of the boundary. I can compute and can write the equality gradient of u equal to j only for x which are on the regular part of the boundary. But the other part is of 0 measure, so I don't care. Okay, so the main point is to prove existence and regularity. So this has these 2 steps, existence and regularity for my shape optimization problem. And now it's classical for those who know shape optimization. And actually the 2 tools I use are due to Dory. First of all, for my shape optimization problem which is there, if I assumed, moreover, that the domain I am considering are in some box, so if I solve my shape optimization problem by assuming, moreover, that my omega are included in some big ball, say, existence would follow by a classical theorem by Butazzo and Dalmaso, because my functional is precisely decreasing with respect to inclusion. So I am exactly in the context where I can use butazole, damazole. So the main difficulty is that I have not this assumption. I do not know whether my minimizing sequence wants to develop some thin parts going to infinity, for example, like for the spectral problems. And so this is why I need to use concentration compactness argument that Doreen explained in the setting of shape optimization problem, completely inspired by the concentration compactness argument by Pierre-Louis Lyons, to deal with the possible behavior of minimizing sequence. And you have basically you have two possible behavior. Either you have compactness, and so the resultant converge, and so you will get existence for such a problem. Or you have dichotomy, it means that you may have two parts of positive measure which goes to plus infinity. And this, in our context, is forbidden because of the constraint. The constraint was that phi of omega is to be less than 1, and you remember that j goes to plus infinity at infinity. So if omega is some part of positive measure will go to plus infinity, this constraint will be violated. So the dichotomy process is not possible. So we have concentration, we have compactness, and so we are able to prove then existence of a set, so which has a very low regularity in our context in shape optimization, just quasi-open set. And at that step, this minimizer is possibly unbounded. So the second step is to prove that it is actually bounded, and it is another tool provided by Doreen recently in 2011, namely the notion of local shaped subsolution, which allows us, we check that the solution of our problem is what Doreen called a local shaped subsolution. I have no time to write it, but you can ask him here for a couple of months. And it implies, in particular, that the minimizer is bounded. But now it's still a very poorly regular set because it's just quasi open. And so we have to work now to prove that it is regular. And the first step in regularity is coming from quasi open to open. You have to start to prove that you have an open set. Quasi open are the level set of H1 function. So since in dimension and H1 functions are not continuous, these are not open sets. And for that, there is a trick which consists in. So you want to make perturbation, and you want to get rid in some sense of the constraint. So instead of minimizing J with a constraint, it's very convenient when you can replace the problem by an unconstrained problem, a penalized unconstrained problem like that, because if you are able to do that, you will be able to make perturbation without taking care of the constraint, of course. And it turns out that actually the two problems, this one and this one, are equivalent for some lambda, and obviously for lambda greater. So there exists a real number lambda 0 for which these two problems are precisely equivalent. So it's not exactly a penalization process for which in a penalization process you need that the penalization parameter goes to plus infinity. Here it will be true starting at some lambda 0, equivalence of the two problems. And to prove that, you need some kind of, so you argue by contradiction, and you need some kind of isoperimetric inequality. If my density J was constant, it would be precisely the isoperimetric inequality. So it's some kind of weighted isoperimetric inequality, which is really useful to prove this. And as soon as you have this penalization, you can prove that the solution U omega extended by 0, obviously, since you work with H10 function, you can extend everything by 0 outside, but you don't know the regularity of your extension. And this allows you to prove that your U omega is indeed Hölder continuous on the whole Rn. And so you have at least an open set, and then you can use classical technique by Caffarelli to get the regularity I mentioned. And now, starting at that point, you are very close to the study that Björn and Henrik did in their paper. Okay, so let me just finish by some qualitative properties about the solution. So my first qualitative property is if I assume alpha homogeneity with alpha larger than 1, then I can prove uniqueness, and it is a very classical way to prove uniqueness, what is sometimes called Lavrentiev principle. So you take two solutions, omega 1, omega 2, you make a contraction of one of these. So for example, omega 1, you contract omega 1 just to be inside omega 2, and you take the limiting value for which you have a contact point. So this is the picture. And you write just down the overdetermined condition at the contact point. You can compare by the maximum principle the torsion function u at t omega 1 and at omega 2. Because t omega 1 is included in omega 2, then the torsion, the u of t omega 1 is smaller than the u omega 2. At the common point of the boundary, they are equal, so the gradient of one is larger than the gradient of the other one. And when you write down and use the fact that you know precisely the gradient, you use the overdetermined condition, and you use obviously the fact that you know the torsion function for t omega 1, which is this one. And so this comparison gives you that G at this common point, x bar is a common point in the boundary, which is gradient of U2 has to be larger than T minus 1 minus alpha G of x bar, which is impossible as soon as alpha is larger than 1. This is where the assumption on alpha comes up. And this argument can be used also to prove, in particular, star shapedness. This is exactly the same argument, because a domain is star-shaped if and only if star-shaped with respect to the origin, due to the fact that J, the constant J is given, your problem is no translation invariant, of course. And the origin, which is the point where J is 0, because J is homogeneous, plays a particular role. And then it's well known that a domain omega is star-shaped with respect to the origins if and only if T omega is included in omega for any T between 0 and 1. So it's a way to define star-shapedness. And so to prove star-shapedness of the solution of your overdetermined problem, you assume that you argue by contradiction, you assume that you have no star-shapedness. You do the same trick, contracting, taking the point where it touches, and you get exactly the same property. So you see that you do not need, you just need homogeneity of J to prove star-shapedness. The convexity is a little bit more complicated, and in particular, to prove convexity, you need homogeneity with a higher exponent. Alpha is larger than 2. And you need obviously some convexity property on the function, on the data. And the data, you will just assume that the one level set is convex. And it turns out that for homogeneous function, it's equivalent to say that the one level set is convex, or some power of J, precisely J to the power 1 over alpha is convex. It's not true in general, but for homogeneous function, it turns out to be true. Then you can prove that omega is convex, and the idea is more or less the same than the one I presented, but it uses a lemma which is true completely independently of this overdetermined problem. So this lemma has its own interest in convexity properties of the solution of some PD like that. And more precisely, what is known is when you assume omega to be convex, and you are just interested in solving the torsion problem. When you assume that omega is convex, it's well known that the level set of U omega are convex. And moreover, it's known that U omega to the power 1/2 is convex. And this is what we use to prove the following lemma. So assume that you have a domain omega, which is this one, and take its convex hull. So with a dashed line, which is there, and take any point on the dashed line. So my point x will be, so in 2D, for example, it will be the convex combination of 2 points x0 and x1, which are on the boundary of omega. This is true for any point which is on the boundary of the convex hull and not on the boundary of omega. In higher dimension, you need just more points. Okay? And it turns out that you can compare the gradient of U omega stars, so the convex hull at point x, with the gradient of U at point x0 and x1. You have this lemma, which is true for any domain, and it's convex hull. Okay? So this is precisely due to the convexity property of square root of U omega star. Omega star is convex, square root of U omega star is convex. So now to prove the convexity, you use the same trick. You take you assume that omega is not convex, like that. You take its convex hull, you shrink the convex hull until you have a common point on the boundary. You write down what you know. You use the maximum principle to compare the solution on this shrinked convex hull and the solution on omega. You write down everything you know at this point. You use this lemma, and you get a contradiction, assuming that g to the power 1/2 is convex. And you need alpha to be larger than 2 to be able to use this.
For harmonic function, it's just without square root, right? And without
For harmonic function, this property stands
for potential.
probably because some at least in 2D, the logarithm of the gradient. No, yes, there is some possible similar result for harmonic function. You're right. I don't remember by heart. Okay, and I finish now with what I give at the beginning, the stability result when you assume J to be not far from a radial function. So, the question is the following. So I recall that J1, what I call J1, is a one level set of my function J. And obviously J1 is a ball, omega must be a ball. It is just what I claimed at the beginning using the rearrangement, because the proof I did for the Saint-Venant problem works as well, because if you replace omega by the ball of same volume, you diminishes phi of omega as soon as J has the property I give. So my question is there any relation between the omega and, for example, J1 or some scaling of J1? And more precisely, I will introduce, so J1, this level set is an open set. I compute the solution of my torsion problem on J1, and I introduce the minimum and the maximum of the gradient of the torsion function over the boundary. And you see, in particular, if J1 is not far being a ball, you expect that these two constants, A and B, will be close one to the other. So obviously, this one is less than this one. Actually, strictly less, because if they are equal, you are in the context of theorem problem. And my theorem is the following. The domain omega is between two scaling of J1, more precisely these two ones. And so the geometry of the one level set of J influenced strongly the geometry of my solution. because of this. And this allows us to claim this stability result of the radial case. This is my last theorem. So just to get an insight, which is maybe more easy to see, if you assume, for example, that each curvature, so the principal curvature of my surface in dimension n, are between r minus epsilon and r plus epsilon, so these are an assumption which tells you that your one level set is not far from a ball, because each of these curvatures are close to a constant. And it is a way I describe the fact that J1 is not far from a ball. Then I am able to say that the distance, the Hausdorff distance between the solution of my overdetermined problem and the ball of radius r is less than some constant depending explicitly on alpha, the homogeneity exponent, the radius, the dimension, and the epsilon, which appears here. So I have basically the Hausdorff distance between omega and the ball is less than constant times epsilon. So this is a new stability result in that context. And I will finish here. Thank you very much.
Question or comments?
Molecularity with their distance is molecular boundary.
Say it again, optimal.
Of the regularity of boundary of domain.
Yes, the regularity I get is only C1 beta because it's linked to the regularity I assume on J. I just assume J to be older. If I want a higher regularity, I need higher regularity there.
So the two dimensions.
And two dimension, more precisely in two dimension, it is completely C1 beta, and in higher dimension, just a reduced boundary is C1 beta.
Is there any, because your G is related to space coordinate?
Yes.
Is it like, kind of, is there some physical application? I mean,
Actually, we were not.
or maybe I ask differently. I mean, do you have any like similar formulation where the G is like more or less independent? I mean, or you give the
Yes.
somehow the
No, actually, the
distribution function of G, for example.
actually the motivation we had was to solve a generalization of the Saint-Benoît problem, where density with a density instead of one, we take a density. So this was our motivation. And, even if Paolo Saleni came with the problem stated like that, okay, I want to solve this problem, I want to know what happens if J is not a constant and so on. But I have not precise physical interpretation of that, except the one of Saint-Benoît.
What about the right-hand side of your PD? If
Yeah.
you will take like some function,
Some F.
which depends on X, let's say, not
Yes.
which is positive, so it doesn't have like complex importance locally then?
Yes. So some parts. So in particular, for the shape optimization problem itself, the fact that you put some F with a reasonable assumption on F doesn't change anything, and you can prove existence of the solution.
And what about the shape of your omega?
So it will strongly depend on F and J at that time. I wanted to mention that to be able to write the optimality condition, you will need also some homogeneity property of F to get this at the end. Otherwise, you are stuck with a Lagrange multiplier like previously. In particular, you see that the one plays a big role at each time I say, okay, if I scale, if I replace omega by t omega, the solution of my torsion problem is just scale 1 over t square u x over t. And it turns out that if you have a general f, it's not correct. So it's only when F has some homogeneity properties that you can have some similar scaling. And the scaling was useful at many, many points.
I have a related question. Can you replace your operator with something more general, say with variable coefficients or with Laplacian, for instance?
So it will be the same kind of answer. So for the shape optimization problem, yes, if you have uniform ellipticity, I think it. I look at Doreen. I think it's the same kind of result. To prove existence, then regularity may be more difficult. And
The shape it's
and to get the overdetermined problem, you yes, you also need the scaling properties, so you cannot take anything as a variable coefficient. No, strongly related to the Laplacian for this last part.
When you're looking at this problem in terms of the parameter, I mean, you have a constraint, and you look at the parameter, can you relax the conditions maybe?
Relax.
The conditions on G.
Relax in what sense at what time?
Well, that you have fewer conditions on, I mean, for instance, this seems to be very strong, right? This homogeneity kind of
Yes.
assumption. And one would assume that that there are other results if you put the constraint, you look at the variable constraints, right?
Mm-hmm.
You look at the minimizers. You don't have only the minimizers, but you have even more, right? You have local minimizers. You can continue even branches which become unstable.
Yeah.
And it might be that you get more solutions, right?
Yes, it's probably possible to and try to follow. Yes, we try at some point to, because we have obviously much freedom even on the constraint we put. Instead of writing phi less than 1, you can put phi less than m, and you have, for each m, you have a Lagrange multiplier lambda m, and maybe trying to play on this m in order to get lambda m equals to 1 at some point. But I'm not really aware of, so I know that there exist, but I'm not really aware of a theorem claiming, for example, that the Lagrange multiplier follow continuously the constraint you put.
No, I mean, it will not be continuous. I mean, not always. I mean, you will have, turning points and so on. Right?
Yeah. It can happen.
It will not be always. I mean,
Okay.
but you still stay with the minimizer. But it might be that if you're staying with local minimizers, you get more, right?
Yes,
So if
I
you
just need
continue
local
with
minimizer, I agree.
Yeah.
Because my argument is
That
just.
will give you more solutions.
Yes, possibly. My argument is just first order optimality condition, so local minimizer would be okay, yes. Yes.
So I think this is related to an earlier question is about non-constant coefficient. What about in the special case, when you consider the special case, instead of Laplacian, you take Laplacian metric with everything that you say carries with a different metric. Say geodesic ball and everything.
Mm-hmm.
Is that the case?
It could be, it seems, at first sight, that you can do that. Yes, let's just say, so I will be more careful to when I want to write down the optimality condition at the end, to see whether this kind of operator gives you exactly what you need. But it's, at first sight, it seems that.
But what do you think about? I mean, you think about a hyperbolic manifold, or? I mean, if it's a compact manifold, then this problem of the
No.
goes away, right?
No, I'm really on
Right,
the
but
whole space.
What I'm just saying is if you just take Rn and add it instead of taking Euclidean metric, take another metric.
Yeah.
It's a simpler problem than what you suggested.
Yeah.
But do everything here goes through that.
At first sight, it seems yes. Yes, my aim was to explain how this method is quite general and you can use it for many overdetermined. Actually, many overdetermined problem. You need some variational formulation there. But yes.
Other questions or comments? Let's thank the speaker
Thank
again.
you.